Hey everybody, I wanted to take just a little more time to speak about types of images. This concept is one of the more abstract and strange things in optics, and it's a pretty important thing to think about. So let's talk about real versus virtual images in just a little bit more detail. So a real image, again, is the kind of image where light rays converge, which means that they meet. They meet in space. You can put a screen there if you want, an index card, a piece of paper, whatever. And we get a so-called real image there. If you look at the picture below, you're going to see that there's a candle flame, and that's actually the back of a concave mirror to the left of it. And on the right, you see a real image of an upside down and larger than the actual candle flame, of real image of the flame. I got to tell you, it is, of course, a little bit more beautiful to see in person, but this is the best we have right now. Here's another example. Now, this is a little out of focus, but that is an upside-down tree. You know it's upside down because there's blue sky below and kind of brown dirt above. That's a real image of an upside-down tree that was outside that window that's off to the right. I was using a concave mirror to produce a real image of that tree. This is actually the same thing that reflecting telescopes do. They just focus on something that's much, much further away. This is kind of a great example. If you look at that little brass weight there by my finger, you'd swear that I'm actually touching the thing itself, but that's actually a real image of it. In fact, you can see two real images of it, one upright and one below, and it's actually, the real thing is down below the thing. You can't even see it there. This is a double concave mirror, and the light is bouncing off the object in the bottom where you can't see it, and it's creating two images right above here close to my finger. Now, this might be a little bit easier to see with some live video. So I'm going to use a candle here, and maybe you can see it just a little bit better. So there's the actual candle. There's the real image of the candle projected out into space. Kind of amazing if you think about it. In fact, yeah, it's actually very, very hot even if you put it where the real image of the candle flame is, because it's the infrared stuff that's also getting reflected, not just the visible light. And if I held that, if I had a little more patience, I probably could have caught that little piece of tissue on fire by putting it where the real image of the candle actually is. Pretty awesome, eh? Now, a little bit more about real images. I think I've said some of this stuff already, but it bears repeating. They are generally upside down. In fact, they're almost always upside down unless there is another optic involved. They can be bigger, they can be smaller, they can be the same size as the original object. It just depends on the distance between the mirror and the object. All of this can be calculated, of course. And as the distance between the mirror and object decreases, the distance between the mirror and image increases. A little bit more about this. I'm actually demonstrating that last phenomenon here. So, up at the top of the screen, there's an illuminated number 4, and I'm holding in my right hand a concave mirror, and you're going to see a gradually increasing in size upside down number 4 on that index card. There it is. And the closer I get to the actual glowing number 4, the bigger it gets on the screen. But notice that there is a change in the distance between my two hands. Okay, now the somewhat more bizarre image, virtual images. These are the types of images where the light rays don't actually converge, but rather they diverge. The image appears inside of the mirror. This is exactly the kind of image you're probably more familiar with, because it's the kind of image you get every time you look in a bathroom mirror. It's exactly what flat mirrors or plane mirrors give us. These virtual images are the types of images where they seem to live inside the glass. The distance is also from the front surface of the mirror. We call it the image distance, but generally speaking, we record it as negative. So flat and plane mirrors always give virtual images, but so do convex mirrors, like convenience store mirrors or blind spot mirrors. They always give you virtual images. That is, the image always appears to be inside or behind the mirror glass. There's an example I showed you earlier. That is a candle and a flat mirror or a plane mirror. Likewise, you've got the guy on the left, he's looking at a convex mirror, and then on the right, that is a real, that's a virtual image of him magnified and distorted. And in both cases, these are virtual images with a convex mirror on the left and concave mirror on the right, where he happens to be standing within the focal point of that mirror. This is worth taking a look at right here. So, you can imagine this is our mirror, and this is our object, which I'm going to move around. Now down here, this is going to be the object. So notice that if I move it around, where the image actually forms changes, and also so does the size of it. And in fact, once I get close to the focal point, the light rays grow more and more parallel, and then when I get within the focal point, it almost seems as though they are forming behind the mirror, and that's what we call a virtual image. I'm going to do this again now that you know what to expect. I'm going to start with a smaller or shorter object. Okay, so let's start this way back here. Object over here, image right there. When I get closer and closer, you're going to see the image get bigger and bigger, further and further away, until right here I'm actually at 2f, 2 times the focal point. Once I pass that critical point, then the image starts to become larger than the object. It's off the screen till I get there. Now, at the focal point, the light rays are emerging parallel. This is exactly what a headlight does. You put a light bulb at the focal point of a headlight, parabolic headlight like in your car, and the light rays come out more or less parallel. It's a little more complicated than that because you don't want the light rays to come out in a straight beam, but rather you want them to kind of diverge a little bit so they cover more area. And then here we are. There you are within the focal point or the focal length of the concave mirror. This is like using a shaving mirror or a makeup mirror or even the inside of a spoon when you get really close to it. You get a magnified upright view that is indeed a virtual image. This is an equation. Don't fret too much. I'm not going to have you use it, but in case you're interested, this equation actually governs all types of concave and convex mirrors. It also works for lenses too, that we shall see in our next big topic. Now, everything so far has been involving mirrors, and this is something I didn't talk enough about earlier, but I'm very fond of asking a question along these lines. So I want you to imagine seeing yourself in an upright, perfectly straight up and down, perpendicular to the ground mirror. How long or how tall does that mirror have to be so that you can see your entire body? Okay, so let's think about that. So if we take a look at this picture right here, this picture actually kind of sums it up. We've got a woman over here, she's staring into the mirror, but this mirror is barely, maybe just around half her height, and that is in fact the case. Why is that? Well, it's the law of reflection. In order to see her feet, she's got to look right here. The light reflects from her feet up to there and to her eyes, and in fact, all she really needs is a mirror just around half her height, and then to see the top of her head, she's got to look just a little bit up here. So that would be directly across from her eyes there. She looks up and she can see the top of her head. So yeah, how tall does a full-length mirror actually need to be? Just about half your height. Now you can easily see yourself in a plane mirror, but you do have to be looking into it within the left and right edges of the mirror. This really is worth talking about a little bit. So let's imagine that this is an overhead view, kind of like if you're on the ceiling of your bathroom looking down. Here is an overhead view of the plane mirror. You want to see yourself in the mirror, you got to be between these dotted lines that are perpendicular to the sides of the mirror. So that's fine. However, another person can see you in a much, much greater range. If you're standing right here, they can see you anywhere over there. A law of reflection. It's a much bigger range. If you're standing right here, they can see you as far over this way, or for that matter, as far over that way. Now, if they go further and further back, that range gets a little smaller because the if you go further back, the range gets a little bit smaller. If they go further back, their range actually gets a little bit larger because these arrows extend out further and further. Now, if you happen to be standing, say, right over here, then they will only be able to see you from, they won't see you much on the left side at all, but they could see you really all the way over there and all the way off screen. So think of this as law of reflection in action. Again, it does depend on where you were standing, but the idea is exactly the same in this overhead view. And that's what I was saying earlier. If you're standing right over here, then they can see you like so. Pretty nifty, huh? A couple of other comments about types of curved mirrors. Concave mirrors, again, have the reflecting surface like so. It's sort of like the inside of a spoon where the light comes in this way. And the convex mirror is the outside of the spoon where the reflecting surface is like so. Concave mirrors, if it's a well-designed concave mirror that is in fact a paraboloid, the light rays will focus into a point or a plane. With a convex mirror, they diverge. They do not meet. They meet for a concave mirror. They do not meet for a convex mirror. Right away you can see why the concave mirrors can form real images, but convex mirrors can never form real images. Also, curved mirrors, they still follow the law of reflection. Really, you could think of a curved mirror as kind of being an infinite number of tiny, flat little mirrors that are connected to each other in this curved shape. Really, you only need I'm only using a few small mirrors over here to depict this. But really, you got to imagine this as millions of itty-bitty, super tiny, flat mirrors that are in the shape of the curve. And in case you're interested, you could follow this link on the PDF, and that'll tell you a little bit more about how lines become curves. And we're going to be getting into greater detail for lenses, but in fact, mirrors behave in a very similar fashion. You have a huge number of very short straight lines, as I was showing you back here. Light rays come in, they bounce down. That's one light ray, or in greater detail, light ray hits up here, bounces down, or a light ray hitting down here bounces up. Then, you multiply that by many rays, and you can get images. However, one thing that's important to think about is if you actually cut the mirror in half, it might suggest to you that you don't get any of this stuff, but in fact that's not the case. Cutting the mirror in half basically just gives you a smaller concave mirror, so you have less light to bounce off of the mirror and therefore a dimmer image. It actually doesn't change the physical characteristics of the mirror at all. If it's a concave mirror, it's still a concave mirror. If it has a particular focal point, let's say 10 centimeters, it actually still has the same focal point. But being half the effective diameter now, you're going to basically get a much dimmer image. If you remember the area of a circle is related to pi r squared, so with bigger radius, the light gathering ability increases as the square of the radius. So that's why if you take a 10-inch diameter mirror, it is almost twice as bright as an 8-inch diameter mirror. Think about that, because 8 squared is 64 and 10 squared is 100. So it's a pretty big difference. People who do astronomy are very familiar with this idea, and they realize that you really do have to have bigger mirrors to get brighter images, which is incredibly important when you have super faint objects. All right, people, that is enough for now. So virtual images and real images. I hope that this makes a little more sense. Okay, see you soon.